Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello students of Senior 6, we are back. I'm Alan and we're still continuing in chemistry on topic of ionic equilibrium. Unit 9, the pH of acidic and alkaline solutions. So today we are going to be looking at lesson 6, which is calculations on the pH of hydrolyzed salt solutions and the action of buffer solutions. I hope you're safe and ready to go on with the lesson. Briefly, before we do a recap, what I expect of you by the end of the lesson, you should be able to, 1, perform calculations on the pH of salt solutions correctly and explain all the assumptions taken during the calculation. 2, illustrate with ionic equations how human blood maintains its pH in the normal pH range even after consumption of acidic and alkaline substances like lemon juice and other basic components. So those are the 2 objectives I want us to work on. If you can fully complete them, then that would be a lesson well taught. So let's do a recap on what we looked at in the previous lesson. We were looking at the hydrolysis of salts, and we had a few examples. As you can see, we looked at potassium carbonate, ammonium chloride, sodium hydrogen carbonate, and aluminum chloride, giving different solutions with different pH. For instance, we noticed that potassium carbonate is strongly basic or strongly alkaline with a pH of around 12. Then ammonium chloride is weakly acidic with a pH of 5, looking at the color of the solution and the pH scale. Then sodium hydrogen carbonate is weakly alkaline with a pH of around 8 or 9, and aluminum chloride is strongly acidic with a pH of around 4 or 3. So that is what we looked at, and we explained exactly what happens that makes the solution to be acidic to that extent. So I left you with the student activity number 5, which I want to quickly go through as you compare with your answers. Question 1 was with well-written ionic equations underlined. Of course, that is the major part in that question. Illustrate why the following salt solutions are basic. Potassium carbonate, which we had already seen its pH, and sodium hydrogen carbonate. So why are they basic? Using the ionic equation. And those are equations. Of course, when you get the potassium carbonate as a salt and you dissolve it in water, it will ionize, giving potassium ions and the carbonate ions. So the presence of carbonate ions in water, they will pick hydrogen ions from water to form an ionized carbonic acid and OH ions. So the presence of OH ions making the solution of potassium carbonate basic. Same applies to sodium hydrogen carbonate as you see the equation. There is one thing I need to point out in here. As we looked at the pH of potassium carbonate and the sodium hydrogen carbonate, you noticed they were different. Potassium carbonate about 11 to 12 as you see the color. Then sodium hydrogen carbonate around 8 and 9. indicating one is a stronger base or stronger alkaline than the other. If you look at the equation, the second equation of the carbonate, 1 mole of the carbonate releases 2 moles of OH ions, whereas for hydrogen carbonate, 1 mole of the carbonate releases 1 mole of OH ions, indicating the concentration of OH ions in the potassium carbonate are higher than those in sodium hydrogen carbonate. And this is the reason for the difference in the pH values as we noted. So that is it we can review in terms of what we had covered previously. Now let's go to today's content, which is the hydrolysis constant KH and the pH of hydrolyzed solutions. I do a quick recap on the objectives. You need to really calculate accurately the pH of different salt solutions and explain the action of the buffer in regard to the pH of a human blood. Those are our objectives. So, hydrolysis constant and the pH of hydrolyzed solutions. Well, as we looked at in our previous lesson, hydrolysis is just the reaction of a cation and anion of a salt with water. And as we looked at, for instance, if you having, let me say, sodium ethanoate, giving ions, and I will include the states later. So you have this as the anion of the salt reacting with water to form an OH ions. So basically what we're talking of hydrolysis is the reaction of either the anion or the cation of the salt. This is just equation, the states, we shall see them later on as we go to our example. So in this case, this equation sets up an equilibrium, and its equilibrium constant is what we take as KH, hydrolysis constant. That is why I needed to bring in here. So from the hydrolysis constant, then the pH can be calculated basing on whether it is there are OH ions or there are hydrozonium ions. Let's take a few examples so as we can understand exactly what we mean by the pH of hydrolyzed solutions. The example is on the slide. We are to determine the pH at 25 degrees Celsius, stating all the assumptions. First, we are looking at number one, we are looking at sodium ethanoate. So by that, what I need to point out is you need to be knowing, is this salt an acidic salt or a basic salt? And that is considered when you look at the formation of the salt. At the start of our lesson 5, we looked at that. So we have sodium ethanoate. When it is dissolved in water, that's what the aqueous implies, it strongly ionizes to form the ethanoate ions in aqueous plus sodium ions in aqueous. It is well balanced. So the presence of these ethanoate ions will undergo hydrolysis. They will react with water. It is an irreversible reaction to form an ionized acid molecules and OH ions. So from that equation, here comes the KH. Like any other equilibrium constant, we get it by looking at the product of the products raised to their stoichiometric ratio. So this would be concentration of an ionized acid molecule times concentration of OH. Remember, they are raised to 1, 1, and since it is 1, 1, neglect it, over the concentration of ethanoate ions. Assumptions. What do I assume in this case? You notice my KH is lacking water, and yet water is one of the reactants. We still apply the principles of chemical equilibrium. So the concentration of water remains constant, both before and after the equilibrium has been reached. And as such, we do not include it in the equilibrium constant KH. So that is the first assumption. The second is when you are looking at this equation, you notice that 1 mole of ethanoate ions is ionizing to give 1 mole of ethanoic acid and 1 mole of OH ions. So the ratio is 1 to 1. So indicating the concentration of an ionized acid molecules is equal to the concentration of OH, since it is the ratio of 1 to 1. Then another aspect we have to look at is what I would call the assumption 3. How do we get the concentration of the ethanoate ions? We look at our first equation. So the concentration of the ethanoate ions are assumed to be equal to the concentration of the salt that has been added in, since this salt, CH3OOONA, is a strong, since this salt is strongly ionizing, so the amount of this in solution directly comes from the salt, the amount of the salt we have dissolved. By looking at the equation, 1 mole gives 1 mole, and this is a strong, it is a complete reaction, indicating the whole of the salt gave into or produced the ions. So these are the 3 assumptions we take when we are calculating the pH. So can we substitute our assumptions in our KH? You'll end up having KH equaling to the concentration of OH ions squared, since this and this are the same, over the concentration of the ethanoate, sodium ethanoate salt before it ionizes. We can now directly determine the concentration of OH. Will be root the amount. Do we have the amount of KH? Yes, it is given as 5.5 exponent negative 10 times, take this the other way. What is the concentration? We have 0.01. Close the brackets, substitute that in the calculator. Very fast. 5 exponent negative 10 times 0.01 root, okay. You'll get 2.34 exponent negative 6. So the pH will be we shall apply the pH of determining pH in bases, which will be 14 minus the pOH. So in this case, we are going to find negative log 10, 2, 3, 4 exponent neg 6. Then we get the pH value. Times 0.01. Negative log answer. So 14 minus the answer, you'll get 8.4. So that is the pH of sodium ethanoate. You can notice this is the pH for bases, indicating this is a basic solution. So that is how you can quickly calculate a question involving pH of hydrolyzed salt if it is a basic solution. Look at the assumptions taken. Let's look at number 2. We're looking at ammonium sulfate. As you could understand, the ammonium sulfate is this comes from ammonium as a weak base and the sulfuric acid as a strong acid. So indicating this is a weak, or what we can call acidic salt. It will ionize to ammonium ions to aqueous. Okay, we add water as an aqueous plus, this is a salt, plus the sulfate ions, aqueous. The same, the ammonium ion in aqueous will react with water to produce an ionized ammonia plus hydrozonium ions. In this case, this will donate a proton to water. Here, this was donating a proton to ethanoate ions. So, balanced here. The KH similarly will be the concentration of NH3 and the concentration of hydrozonium ions over the concentration of NH4+. Same principles, very, very fast. Same principles. The assumptions in here, water remains constant. So, very fast, then I will leave you to finish up the calculation. If you look at this, you notice that the concentration of ammonium ion is twice, since it is 1 to 2. 1 mole gives 2. It's twice the concentration of ammonium sulfate salt. That is one assumption you have to make or to take note of. And from here, the concentration of ammonia is equal to the concentration of hydrozonium. So you substitute like as we did. I will leave that for you to continue. Please continue on that. You should get the pH as 4.1. Please continue on that and finish it up. Continue on that and finish it up. That should be the answer here. Substitute, just simply substitute. The assumptions already highlighted. Just bring the assumptions in here and follow the procedure. Follow the procedure. The difference in here would be you would directly get the hydrozonium ions, the concentration of hydrozonium ions, whereas here we found the concentration of OH ions, then we substitute in the formula. But here you will get the hydrozonium ions, then you substitute in the formula. Simple, keep, calculate and finish it up on that. I'm leaving that for you. Keep, complete it. So with the 1 minute for you to complete, we can look at the quick exercise. That is the exercise 5 I'm leaving for you. Please ensure you go on and practice them. Without you practicing, you will not really understand how to go through it. This is part of your learning. Practice them. Let's look at the buffer solutions. Let's look at the buffer solutions. Buffer, I think the word buffer is not new. Most of you use the word buffer, but let's look at them. What are they? A buffer solution is the one which resists changes in its pH when a small amount of the acid or base is added to it. Let's look at the illustration in here. When it is water and you add an acid or a base, directly that solution will be acidic or it will be basic. But when it is a buffer and you add a small amount of the acid or base, then the pH does not change drastically like how it does with water. So such a tendency makes that solution to be a buffer. I want to raise this point to you. Small amounts of the acid or an alkali, small amounts. When you add excess, then the pH changes. Small amounts. There are basically two types of buffer solutions. We have the acidic and the basic. Acidic maintains the pH less than 7, that is in the acidic range. Then basic, they maintain the pH in the pH above 7, and that is the alkaline range. Depending on what makes up the buffer, then they still can be acidic or basic. Acidic buffer is made up of a weak acid and its conjugate base. What do I mean when I say conjugate base? The salt from a strong base. For instance, you have ethanoic acid with sodium ethanoate. Ethanoic acid is a weak acid. Sodium ethanoate is the salt of the weak acid, but from a strong base, sodium hydroxide. So you have sodium or hydroxide reacting with ethanoic acid to form sodium ethanoate. This is a salt of a strong base and a weak acid. So that's what we mean. You have a solution of a weak acid with its salt from a strong base. And there was carbonic acid with the sodium hydrogen carbonate, the same principle. Then a basic buffer has a weak base with its salt also from a strong acid. Example, ammonium solution with ammonium chloride. I think you understand there. So the two buffer solutions, for instance, one has a pH of 4, indicating it is acidic, another has a pH of 10, indicating it is basic. So after understanding what exactly composes those buffer solutions, can we look at how they work, the action of the buffer solution? I will give you an example here. Normally in Rwanda, around a lake, they always give what they call the buffer zone for between distance of 50 meters away from the lake. The local people normally call it mirongitano. So there is that buffer zone. That buffer zone, how it works exactly is simple. If water expands, or there is a lot of water in the lake, the property for the local people is not affected because they've not encroached in that buffer zone. And when water recedes back, then the soil is not moving along with the water receding because the area along the lake has been maintained with a vegetative cover. So the water is maintained with high quality and there is no silting in the lake. That is the example of the buffer zone. But in chemistry, when we talk of the buffer solution, for instance, the acidic buffer, it also has such a properties. It changes when an acid is added or a base is added to make sure that the pH remains constant. Let's see the illustration of acidic buffer with a pH of 4. With a pH of 4, what happens if you add OH? The OH will be reacting with unionized acid molecules. So as the OH, which would bring the solution to be basic, would be removed. If you add a hydrogen ion, then it will react with the ethanoate ions, forming unionized acid molecules. In that case, the effect of the acid or the hydrozonium added will be neutralized. That is how the buffer works. How applications of the buffer, basically they are, as I said, they are applied within our body. The blood is able to keep its pH at 7.4, and the illustration is clearly indicated. Hope you will understand that. Thank you for your attention, and thank you for being part of the class. Please keep safe. We meet next time.